Hello and welcome to part 3 of OpAmps, in which we will be looking at positive feedback. That's when a sample of the output voltage is fed back into the non-inverting, or the input with the plus sign next to it. We'll start by considering this circuit and asking, what would the output be if you just switched on this circuit, turned on its power supply and left it? The answer is quite an interesting one. The answer is, it's impossible to tell. Why? Well, because this output could be in one of two stable states. First, consider what would happen if the op-amp was in a positive saturation state, which means that its output would be at its positive rail, at the plus 12 volts, the maximum output that this op-amp could give. In that case, you would have plus 12 volts here on the output, which would mean that you would have plus 12 volts on the non-inverting input. You would have 3 volts in this case on the inverting input. The action of the op-amp is to put its output equal to a very large number called the open loop gain times the difference between these two inputs. In this case, that would be a very large number times 12 minus 3, or a very large number times 9. Well, that's a positive quantity, which means that the op-amp is, with these inputs, going to try and keep its outputs at the maximum possible it can, which in this case is plus 12 volts. So this is a stable situation. However, consider what would happen if the op-amp's output was in negative saturation, at minus 12 volts. In that case, we would have this situation. Minus 12 volts on the output, which would mean minus 12 volts on the non-inverting input. We've still got 3 volts on the inverting input. Now, the output would be the open loop gain times the difference between the non-inverting and the inverting inputs, which is now minus 12 minus 3, which is minus 15 times A. This is a very large negative quantity, which means the op-amp would be trying to keep its output at its minimum possible level, which is minus 12 volts, its negative power supply. So this is a stable situation as well. So if the op-amp was in this state, it would stay there. And if the op-amp was in this state, it would stay there. It's got two stable positions to be in. And it's impossible to tell which one it is unless you know a lot more about the details of the internal structure of the op-amp and what happened in the circuit while you were turning it on. Now, you might wonder, what is the point of a circuit which remains either at plus 12 volts or minus 12 volts all the time? And the answer is not much. But if we make a slight alteration to this circuit, then we end up with a circuit which actually is very useful, something called a Schmitt trigger. And the alteration that we make is to reduce the amount of feedback that we give. So instead of connecting the non-inverting input directly to the output, we would only feed back a proportion of the output. Standard way to get a proportion of an output voltage is everybody's favourite circuit again, the potential divider. So the circuit that we'll be investigating is this one. Take the output, feed it through a potential divider, take the output of the potential divider and use that as our positive feedback, and put our input there into the inverting input of our circuit. And now we have a circuit with much more interesting properties. For example, consider these resistor values. We've got 30k as our feedback resistor and 10k as a resistor from the non-inverting input down to ground. So our potential divider has 30k here and 10k here, which means that our non-inverting input is going to be 1/4 of V out. If Vout is plus 12 volts, this is going to be at 3 volts. If Vout is at minus 12 volts, this is going to be at minus 3 volts. So this is going to be 3 or minus 3. And now something interesting happens if you allow Vin to vary. Note that if Vin is greater than 3 volts, then it doesn't matter if Vout is plus 12 or minus 12, Vin is always going to be greater than the voltage on the non-inverting input, and therefore V plus minus V minus is always going to be negative, which means the output will go to minus 12 volts. So we know that this circuit, Vout, is minus 12 volts for an ideal op-amp if Vin is greater than 3 volts. If Vin is less than minus 3 volts, then again, it doesn't matter which saturation state the op-amp is in. Vin will always be less than the non-inverting input, which means that V plus minus V minus will always be positive, and therefore Vout will go to 12 volts. So Vout is always 12 volts if Vin is less than minus 3 volts. What if Vin is somewhere in between 3 volts and minus 3 volts? Well, if the op-amp is positive saturation at 12 volts, so that the non-inverting input is at 3 volts, then if Vin is somewhere between minus 3 and plus 3, the non-inverting input is going to be still bigger than Vin, so Vout will remain at plus 12 volts. On the other hand, if Vout was at minus 12 volts, and Vin was somewhere between 3 and minus 3 volts, then Vin would always be above the value at V+, and therefore V plus minus V minus would still be negative, Vout would still be minus 12 volts. So, if Vin is between minus 3 volts and plus 3 volts, then Vout doesn't change. It remains in whichever state it was in before. We've built a circuit with memory. Effectively, it is remembering whether Vin most recently went above 3 or below minus 3. And it's remembering that information. We can see how this works on the simulator. I've built the circuit here, so you can see the voltage at the non-inverting input as well as the output voltage. At the moment, this op-amp is in positive saturation at plus 12 volts. But we know that if the input voltage here goes above 3 volts, then suddenly the output flies down into negative saturation and the non-inverting input will go down to minus 3 volts. And if I go back to 0, it will remain quite happily at minus 12 volts, and it will stay there until the input gets down below minus 3 volts, at which point the inverting input will be below the non-inverting input, and then the op-amp will go into positive saturation again. There it goes. And it will stay in positive saturation. Doesn't matter what the input voltage is, until the input voltage gets back to 3 volts, at which point the inverting input would be above the non-inverting input, and the op-amp would go back into negative saturation. And so on. Now, it's quite a curious, interesting little circuit, but it does have a very useful real application. And that is in the interfacing of analog signals, often quite noisy or slowly changing analog signals, into a digital circuit. For example, let me modify this circuit a bit. I'll stick in a sinusoidal voltage source there, And I'll also stick in another variable voltage source there and connect that down to ground. Okay, so the input voltage, oops, wrong place. That'll do. Right, so the input voltage is now the sum of these two sinusoidally changing voltages. Let me put another voltmeter on the input itself. And I will turn this sine wave here up to 5 volts and turn this one off to 0 volts. So we have a 5 volt varying sine wave going in, and we can see what the output is going to be from our Schmitt trigger circuit. Probably don't need this 3 volt one anymore. Let's get rid of that. And I'll put this in the transient simulator so we can see the effect of what's happening. Okay, let's say go. That's probably quite enough. I'll zoom in a bit so you can see what's happening. And we have a sine wave coming in. As you can see, when the sine wave gets below -3 volts, the output suddenly shoots up to +12 volts, and it remains above 12 volts until the sine wave gets to +3 volts, at which point the output flies back down again, and so on. Why is that useful? Well, if we didn't have the Schmitt trigger, if we didn't have that positive feedback, the circuit would do this. It would change its output from positive to negative saturation whenever the input sine wave crossed 0, because now the op-amp is just comparing the input voltage on its inverting input with 0. So if this signal is above 0, it will output -12. If this signal is below 0, it will output +12. And if this was an input to a digital circuit, and if this was, for example, being used as a clock for the digital domain, then that would work fine, except that any real signal from the analog domain is never going to be perfectly noise-free. If I change this second source here so that it wasn't a pure sine wave, but if I change it into a noise source and maybe give it a value of 1 volt RMS per root hertz, we'll talk about the units of noise much later. What this is effectively going to do is put a 1 volt random signal on top of the 5 volt sine wave. So, we'll run it again. You can see we now have a very noisy sine wave. And we now have a rather unpleasant looking digital signal that results. And that's because if we zoom in and have a look at that in a bit more detail, you'll see that the addition of the noise to this sine wave here causes the total voltage here to drop below 0 and then come back above 0 and then drop below 0 and above and below and above and below and above and so on quite a few times, while the sine wave is still just going down. So instead of a nice clean transition from low to high in the digital domain, we get this bouncing, as it's called. And if this was going to be a clock signal, then anything that's being triggered by this clock is likely to be triggered multiple times. That's not very helpful. Solution: put in our bit of positive feedback, build a Schmitt trigger, and now the noise is not causing any bouncing of the digital signal at all, because the output only goes high when the input gets to below -3 volts, and it doesn't go back low again until the input gets to above +3 volts. Net result, a nice clean digital signal from a rather noisy analog signal. That's the end of this one. Next time we'll have a look at how you build a practical amplifier with an op-amp.